Right, good morning. Welcome to our lecture where we are continuing with section 4.7 on improper integrals. Just confirm to me that you can hear me clearly so that I'm sure that we are all on the same page. Can you hear me? I'll assume that you can't hear me. Okay, thank you. Is it clear? Okay, all right. All right. So we are looking at chapter 4.7, uh, which is on improper integrals. And yesterday we talked about type 1 integrals. So just to recap on that, so we said an integral is an improper integral of type 1 if you've got a function defined on that, and if the limit as t tends to infinity of this exists and is a real number, then we then say that the integral from a to infinity is convergent. Otherwise, it is divergent. And the same applies to a function that is defined from minus infinity to some value a and going to r, such that if the limit as t tends to infinity of the integral from t to a of f of x dx exists, so if the integral exists and it's a real number, then we then say that improper integral is convergent. Otherwise, it is a divergent integral. Right, and then we also then looked at the p-test, and we said if you've got an integral I, which is the integral from 1 to infinity, then of 1 over x to the p dx, then is going to be convergent if p is greater than 1 and diverges if p is less than or equal to 1. And here we used 1, but it actually works in general that if you've got any number that is greater than 0, then it is going to work. So that is the p-test there. And now we are going to look at some improper integrals of sort of type 1, and we will see how we can solve those ones. So we looked at one where you've got either infinity and a number there, or a number there and minus infinity, right? So the question is, what if we've got minus infinity to infinity? What do we do? And the answer is, we look at this definition. So if you've got a function which is defined from r to r, and if for some r, so this is for some r, for some a in r, that the integral from minus infinity to a of f of x dx, and the integral, there's some missing text there. Let me just write with this, f of x dx. If these both are convergent, then we then say that the limit or the integral for this would be the sum of that plus that, right? So this, you can only look at this, you can only say this is equal to that, to the sum of those two, if both are convergent, right? So if we get a real number there and a real number there, then we can then say the integral is the sum of those two. And then, so what it means is if this integral is going to be divergent, if and only if, so if one of the integrals is divergent, the ones that we are supposed to sum here, if they are convergent, if one of them is divergent for some a, then we then say it is going to be a divergent integral. Right, and then if it is convergent, then it is going to work for any c that you pick, right? So here we then say, remember we are saying for some a, if this works, then we say it's convergent. But if it happens that it works for some a, then it is going to work for any a that you pick that is a real number, that these we should be convergent, because if one of them becomes divergent, then we are in this case, which would contradict the fact that the integral is convergent, right? So this, if it works for one c, it's going to work for any c that you pick, right? And one other thing that you need to note is the fact that if we have got an integral from minus infinity to infinity of f of x dx, it is not going to be equal to the limit as t tends to infinity of, if you put t there and minus t there, f of x dx. And this, you can see that it's not true by looking at example 4.7, number 4 of the exercises. So exercise 4.7, number 4, it will show you that indeed this is not true in general, right? Okay, so here we are not going to do an example. You can look at that example to just see that this doesn't work. Intuitively, you might think it will work because t will be going to infinity, so this will be going to infinity and that to minus infinity, but it actually doesn't work. Right, so now we go on to another test. So yesterday we looked at the p-test and we saw that certain integrals of this form we can determine by just looking at the power here and determine if it's going to be convergent or not. Now we are going to look at what is called the comparison test. So just to give a bit of motivation on why it would work. So suppose you've got a function, you've got two functions actually, and they start on the same sort of value. And so you've got this as your y is equal to f of x. And then you've got another one, which is y is equal to g of x. Right. And so if you think about these two functions, you can see that from a going that direction, from a onwards, y of f of x is greater than g of x, right? Or it's the other way around, sorry. It's the other way around, right? The value, if you pick any value here, the value there will be less than that one, right? And so the idea is, if that happens, then if you think also about the area under the curve, which would be the integral, right? Then you'd see that we know from the comparison theorem from 114 that if we think about the integrals, they are going to be less than the integral of f of x will be less than the integral of g of x, maybe less than or equal to, right? So we know this. And so now what we want to see is how does that affect convergence and divergence. So if this is the case, then if this function, so if this integral is convergent, and so what it means, convergent means that it exists and it's a real number, right? So it would mean that because this one is also less than or equal to that, it should also be convergent, right? If the bigger one is convergent, then the smaller one should be convergent, right? And then the other scenario is when we know something about f of x. So if f of x is divergent, right, then it would also mean that g of x should also be divergent because it is bigger than a divergent integral, right? So the integral there should also be divergent just by thinking about comparing, right? So that is the idea here, to say if I know that the area under the if the area under here is giving us an integral that is going to be divergent, then even for g of x, it's also going to be divergent. All right, so let's see, let's put it more formally. So this is the comparison test. For improper integrals. For improper integrals. Right, so what does it say? So it is a theorem. It says let f and g be two functions that are defined on this same interval, and they go to R, and suppose they are continuous, and then suppose that for some c greater than a, right, we have that f of x is less than or equal to g of x for any value that is greater or equal to c. So the c that is being talked about is what we are calling a in this scenario, right? So if this happens, then the following is true. Then the following is true if the integral from a to infinity of g of x is convergent, then the integral from a to infinity of f of x is also going to be convergent. Right, and as I had mentioned, you'd see that if we think about this, then you've got something like this. If you take the integrals of that, this is an a, so from a to infinity of f of x would be less than or equal to the integral from a to infinity of g of x dx. And this, if we know that this is a real number, then this is also going to be a real number. And then there's a question, if it was minus infinity, would we need to use the smaller function? I'm not sure what you mean by that. Maybe elaborate more. what are you calling minus infinity? Are you talking about the integral here of g of x or of f of x? Maybe elaborate more there. And then the second case is if the integral from a to infinity of f of x dx is divergent, then we will have that the integral from a to infinity of g of x should also be divergent, is divergent. Then, so what we need to note in these two cases is if you've got an integral from f of, from a to f from a to infinity of f of x dx is convergent, then we don't know anything about what happens to the other integral. Then we can't say anything about the integral from a to infinity of g of x dx. So if you've got a scenario like this and you know that this is convergent, then you don't know if this is going to be convergent or divergent. It could be either, right? That's what the statement is saying. And then if the integral from a to infinity of g of x dx is divergent, then we can't also say anything about the integral from a to infinity of f of x dx. So this is just to guide us such that when we are trying to find appropriate functions, we know that we sort of know the type of function that we want to get. So if you create a system where this happens and then you know that the integral of this is divergent, then you can't say anything about f of x, right? So you would need something better than what you would have chosen there. Suppose you wanted to know something about the integral of f of x, but you know that this is divergent, then you can't say anything about f of x. The same applies if you know that f of x is convergent, then you can't say anything about the integral of g of x. So when you're trying to find the appropriate functions, we'll see when we do examples, you have to pick them carefully there. Right. So that's the case. So let me look at the chart. So the question is, so if f of x is convergent on on minus infinity to a. Okay. All right. So you are talking of a scenario where we are not looking at something like this. So this can be what I can just say is this can be replicated to the other side here, right? If you've got g of x on top of there, and then you've got your f of x at the bottom there, then you can sort of say the same things that we have just said. If the integral um, from minus infinity to a is convergent, then this one is also going to be convergent and on the same bounds. And if the integral of f of x is divergent, then the integral of g of x is divergent, because the idea is the same. What is just changing is the fact that now we are going on the other direction. I hope that clears that. Right. So so we've got these scenarios, and here, if you look at the comparison test, when you find out that one function is, well, when you decide, suppose you were in this scenario and then you knew that g of x, the integral of g of x here is convergent, and the integral of, and then you conclude that the integral of f of x is convergent. In this case, we don't know what the integral is, right? And we probably might not be able to determine exactly what is the value of the integral. But then that's when we see that if this happens, so if you use the comparison test and you find out that the function is convergent, then we can then employ numerical integration to be able to estimate or approximate what the integral is, right? So something to just note that if we use the comparison test and we find out that the function is convergent, then we can use numerical. I think it's in one WTW 123 where they do numerical integration to then find to be able to approximate the integral. Approximate the integral, right? So it tells us when it's convergent. This one just tells us where it's convergent, and then we can then use other ideas to be able to determine an approximation of the determinant. And then if it's divergent, there is no need to find the integral, because we know that the integral either is infinity or doesn't exist. So there is no need to proceed after that, right? Okay, so let's look at an example. So the example that we have is an integral from 1 to infinity of x cubed plus x squared over x to the 4 plus 1 dx. Right, so here we've got this integral, and then we want to determine if it's going to be convergent or divergent, right? So what do we do? So we look at the so if you've got a rational polynomial like this, you look at the highest power of the numerator and then the highest power of the denominator, right? So in this case, we can see that the highest power is x cubed of the numerator, and then of the denominator is x to the 4, and if we divide the 2, we get 1 over x. And here, so the idea would be to say, well, if we are able to say this, and we know something about the integral of this one, then we will be able to then perhaps find the integral of that one, right? So we have found out that the highest power is that divided by the highest power of that, and then we get 1 over x. And we know that the integral from 1 to infinity of 1 over x dx diverges. And what is the reason? The reason is this is by the p-test, right? With p equal to 1, right? So if you think about the power here, it's to the power 1, so p is equal to 1. And if we use the p-test, we see that this function diverges. So if we are able to show that this is greater or equal to some it's greater or equal to some multiple of 1 over x, then we can then use this and then conclude that the integral there is also divergent. So what we want is to be able to find x cubed so whenever we do comparison test where we sort of suspect that our function is going to be divergent, we want a scenario like this where we know something about this and then we then use to conclude something about the integral of that one. So this would be our strategy or our plan to be able to do this, and then we then find ways to solve it. So strategy is this, and we want that k of x we know is related to 1 over x, so we know it's going to diverge, right? So how do we do that? So if we look at the numerator, we can see that it's x cubed plus x squared, which we know is going to be greater than x cubed, right? This value is always a non-negative value, so if we add it to x cubed, it's going to be greater or equal to x cubed, right? And then if x is greater than or equal to 1, so remember that we are integrating from 1 to infinity, so we can assume that x is greater or equal to 1, then we know that x to the 4 is greater or equal to 1, right? Any value of x which is greater than or equal to 1, if you take its power to the 4, then it's obvious that that happens, right? So if I take 2 of these, then they are going to be greater than 1 plus x to the 4. So I just added x to the 4 on both sides, and then I end up with this. And from there, I can then say if x is greater or equal to 1, then I'm going to have x to the 4. Okay, I think okay, well, it will work, right? I thought I made a mistake. Okay, so it should work. So x to the 3 plus x squared over x to the 4 plus 1. So what I created here was the denominator, right? So this is going to be greater or equal to, so the numerator is greater than that. And then the denominator, remember that the denominator, which is that, is less than or equal to that. If you take the reciprocal of these, right, it would have looked like this: 1 over 1 plus x to the 4, right? So we can safely say that this would be greater or equal to 2x to the 4, right? And then I know that this is greater than 0 because we are dealing with x greater or equal to 1. And I can then say, so this x cubed plus x squared plus x4 to the 1 can be rewritten as half of 1 over x, right? I take the 2 there, and then I evaluate or simplify, and then I get that, right? And then we now consider, so basically half of 1 over x is our k of x here, right? So we now consider the integral from 1 to infinity of half of 1 over x, which is obviously going to be half. We can take out the scalar there, and then we are left with that. So we know that if this diverges, obviously half of that would also diverge. So note that p is equal to 1, and so by the p test, so here let me just point out that here this was like our strategy, so it's not part of the proof itself. We're just thinking about what to do. So now we are writing formally, so that's why we are now sort of repeating what we had on top there. So by the p-test, the integral from 1 to infinity of 1 over x dx diverges, and so therefore half of the integral from 1 to infinity of 1 over x also diverges, right? And then thus since that diverges, it will follow. So it follows that the integral from 1 to infinity of x cubed plus x squared over x to the 4 plus 1 dx also diverges. And this is by the comparison test. So whenever you're answering this type of questions, make sure you identify the test that you are using, so that you're not penalized, because if you don't identify it, you'll most likely be penalized. So take note of that. If you use the p-test, state that you are using the p-test. If you're using the comparison test, state that you are using the comparison test. Right, so that will be the solution to that one. Right, so that's one question we are going to look at. Now we get into type 2 improper integrals. Right. So type 2, in these ones, we get discontinuities. Remember that one we had our bounds going to infinity or minus infinity. Now we have got something different. So discontinuities okay in these ones. So let's see. Let f, or maybe let me say if f is continuous on AB, so it's a closed interval like that, but not at B, right? Or maybe let me just put an open there, but not at B, then, so it's continuous everywhere else, but except B, then we can say the integral from a to b of f of x dx is going to be the limit as t tends to b from the left of the integral from a to t of f of x dx, right? So this becomes our definition for the integral there, and this is provided provided that the limit exists and is a real number. So we want it to exist and to be a real number. And then in this case, so if it exists and it's a real number, then we say the integral is convergent. Right. Let's look at the second scenario. If f is continuous on there, but not at A, then we've got sort of the same definition. The integral from a to b of f of x dx is going to be the limit as t tends to a from the right of the integral from t to b of f of x dx. And again, this is provided that the limit exists and is a real number, and then again in this case we say the integral is convergent as expected. Right. And then we've got a third scenario in this type 2 ones. If you've got so if the discontinuity is not on the end points but inside the interval, so if that is continuous on A to C and on C to B, but not at C, so discontinuous at C, then the integral is going to be from A to B, f of x dx is the integral from A to C, f of x dx, plus the integral from C to B, f of x dx. And again here, so here you would apply the first definition in 1, and then here you would apply the second the other definition in 2, right? And here again we've got provided that both are convergent. Right, so we've got those 3 scenarios. So just to note, if in the third scenario, if this converges and, so the and here is important, the other one also converges, then that is when we say the integral from A to B of f of x converges. Right? Now, if either one of them diverges, then we would expect that the whole integral also diverges. Right. Okay, so those are type 2 ones, and we are going to look at maybe 1 or 2 examples if time permits, and we'll see how to evaluate those ones. So example number 1, suppose you've got an integral from -2 to 2 of 1 of x, or 1 over x dx, and you want to find out what is the integral here. So we want to find the integral there. So the integral from -2 to 2 of 1 over x dx, so if you look at this, you'll see that 1 over x is not going to be continuous at 0, at x is equal to 0. So that is a point of discontinuity, and that is the only point of discontinuity. So what we have to say, we have to separate the 2 and say this is that plus the integral from 0 to 2 of 1 over x dx. And now we look at this integral. and see what happens. So if it converges, then we have to check the other one. But if it diverges, then we know the whole function is going to diverge by the definition that we've been given. So we've got that, and then the limit. So by definition, this is going to be the limit as t tends to 0 from the right of the integral from t to 2 of 1 over x dx. And this is going to be equal to the limit as t tends to that of the natural log of the absolute value of x from 2 with the bounds t and 2, and that is going to be the limit as t tends to 0 positive there of the natural log of 2 if we evaluate, if we put in the values, minus the natural log of that. And we've got, so we can simplify this to, we can remove the absolute values because both of the values are going to be positive. Remember that t is greater than 0 in this case because we are approaching t from the right? So we are talking of positive values going to 0. And then, so this is just a constant, but this is going to be, so if you think of the natural log of t, it is, if you're approaching 0, then it goes to minus infinity, and so therefore we get that as infinity. If you just want to see what's happening, if you draw the graph of the natural log of t, you'd see that it looks something like that. And then if you want this one, then it would look something like that, right? So this would be y is equal to the natural log of t, and then this one is y is the minus natural log of t. So if you are approaching 0 here, you can see that this goes to infinity. And so that's how we get that. And so what does that mean? It means even though the limit exists, it's not a real number, so it diverges, the integral diverges. And once one of them diverges, one of the two here diverges, we can then say the integral from minus 2 to 2 of 1 over x dx diverges also. Well, you can add since this one diverges, and that is the solution there. Right, so that is the story there. Let me quickly look at another example, which is a fun one, I think. It's not really asking the integrals, but it's us just checking if you see what's happening. So we want, you want to write this integral as a sum of 4 limits. So you're asked to write this integral as a sum of 4 limits, and let's see how we can do that. Right, so the integral from 0 to 4 of that can be rewritten as, if you factorize the denominator there, then you see that it's just x minus 1 and x minus 2 dx there. And so you can see that you've got 2 points of discontinuity. X is equal to 1 and x is equal to 2 are going to be a problem here. So we want to, when we are making our limits, that's the points that we want to deal with. Right, so from here, we can then say, so we know these 2 points are not supposed to be, well, they should be endpoints when we are looking at our integral. Okay, so maybe let me just draw. So we've got 0 there, we've got 1, we've got 2, and then, so these are the endpoints, and then these are the points of discontinuity. So if you're going to write this integral as a limit, as a sum of 4 limits, you want something with 0 and then perhaps 1, and then, okay, so what we want is to be able to say from 0 to something, x minus 1, x minus 2, like that, plus the integral. So if you start with 1, then you want a 1 there, and then dx x minus 1, x minus 2, and then plus something, and then plus the last one. So this will be dx x minus 1, x minus 2. And then this one should be 4, because that will be the last one, so that we cover all the whole interval there, x minus 2. And then, so we need to determine what we should put there, 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 and there. So if we were to put 2 here, then we are going to have a problem. Why? Because we now have point of discontinuity there, point of discontinuity there, right? Based on what we, based on the definitions that we have, right? We don't want to have 2 points of discontinuity for one, or for one integral. We want to separate them. So we should probably have avoid 2 there and put maybe 2 there, right? And then and once we've got a 2 there, we can put 2 there, because 2 will just be the only point of discontinuity here. And then from then there and there, we need some other value, which is not 1 or 2, so we can pick whichever. I picked 1.5. You can pick any other value that you feel will work. As long as it's not 1 or 2 and it's between that, it should be fine. And then now we are able to write this as a limit, as we have been asked to do in the question. So that becomes, the first one here becomes dx x minus 1 over x minus 2 plus the integral from 1, we actually want the limit here from t tends to 1 from the right of the integral of t to 1.5 of that, x minus 1, x minus 2, and then the third one is the limit as t tends to, so here we want it to go to 2 from the left of the integral from 1.5 to t dx over x minus 1, x minus 2, and then the last one is the limit as t tends to 2 from the from the positive of, or from the right of that, this should be t there, to 4 dx over x minus 1, x minus 2. And so we have managed to write this as a sum of 4 limits, as we were supposed to do. Maybe I will give you an example that you need to look at. So go and find out I think it's in the textbook, but you can just do it based on what we have done so far to see how you are doing. So you want to find the integral from 1 to 3 of that dx. So here the point is just to write this differently, so you can write it as x minus 2, meaning that the points of discontinuities our function is not defined for these 2 points, and so therefore when you are writing your integral you should consider that it's continuous on any other point that you pick from 1 to 3, except when x is equal to 2. So remember that this is not in the interval that we are given 1 to 3, so we just need to deal with this one. So the integral will be 1 to 3 2x squared over 2x dx should be written as from 1 to 2 2 over x squared minus 2x dx plus maybe let me write it here, the integral from 2 to 3 of 2 over x squared minus 2x dx. And then you just say this is the limit as t tends to 2 from the negative of 1 and t there, x squared minus 2x dx, plus the limit as t approaches that from the right of t to 3 of that. And then you just use what you know already. I think from here it should be clear what happens. This is dx there. So you rewrite this, you do your partial fractions, and then you can then find the integral for that and that for that, and then you add, and then you see what happens. Or maybe you just need to check one of them. If you see that it's infinity, then you know that it's going to be divergent. I will stop here. Thank you for your time, and enjoy the rest of your day. If you have questions, I think I'll be here for a minute or so just to make sure that we are all on the same page. Otherwise, enjoy the rest of your day. Thank you. So there's a question, why was the previous one a sum of 4? So the question asked to just write the integral as a sum of 4 limits. That was the instruction in the question. So that's why we've got a sum of 4 limits there. Does that answer the question, or did I miss something? Okay, so we were not asked to evaluate the integral. It was just write that as a sum of 4 limits. The point was also, if you're given something like this and then you want to find the integral, the logical step to take is to write it as a sum of 4 limits before you start trying to find the integrals of each. Yeah. Okay, I think there are no more questions. Thank you for listening, and enjoy the rest of your day. And all the best with your class tests if you haven't written yet. All right, bye.